All right, can you all see this?
Yep.
Okay. Oops, let's try to get my pointer. All right. Hi, everyone. My name is Guy, and I'll be telling you about some joint work with Neha, Jane, and Leung on, as Brian said, decision tree splitting criteria, theory, and applications. Okay. Decision trees are used all over computer science. So just two examples here. In machine learning, decision trees have historically been an extremely important model class. And still today, they're very useful. They make very interpretable models. And also, they're fast to evaluate relative to the number of parameters in the model. And then in algorithms complexity theory, decision trees encode algorithms that make few queries to the input. So if you want to know the query complexity of a function, how many queries it takes to evaluate it, you naturally have to look at decision tree representations for that function. And just so we're on the same page about the decision trees we're talking about, in this talk, we'll consider all our functions to have Boolean inputs and Boolean outputs. And then decision tree has internal nodes, each of which encode a single variable. And then based on the bit of that variable, so here the 7th bit, we'll decide to go down the left or right subtree until we eventually reach a leaf, which the decision tree then outputs. So this is the encoding of some function in decision tree form. This talk is motivated by a disconnect between the theory and the practice of building decision trees. So there's a lot of practical work from the machine learning side in terms of how to build decision trees. And the algorithms used here in practice tend to work top down. So they kind of first decide what's a good variable to put at the root. And then once they make this decision, they decide how to build the tree underneath it. And these algorithms tend to be empirically successful. Some names you might have heard about are like ID3, C4.5, and CART. And well, if you look at their citations, they collectively have on the order of 100,000 citations. So they've been widely used. But we don't have really strong theoretical performance guarantees on how these sorts of algorithms work. On the theory side of building decision trees, so one strand of work has been trying to show the NP hardness of building kind of the best decision tree. And there are different formulations, but roughly they say something like, if you have access to a function and you want to know like what is the smallest decision tree that computes it, then this is NP hard. There is still work on building decision trees. It doesn't get polynomial time, it doesn't get kind of the optimal decision tree. But for example, so the fastest algorithm, this is also used in a learning setting for building decision trees, Ehrenfleit-Hausler, proceeds bottom up. So it kind of starts, before it knows what to put at the root, it first has to check everything beneath it. So just like very different between these two. And this disconnect will motivate us in our search for algorithms with provable guarantees, but that look more like this top-down, these sort of top-down algorithms, and we'll then get some nice applications of that. Okay. So just to reiterate, kind of the fundamental question underlying this talk is, given access to some function, can we efficiently build a decision tree that well approximates that function? And we'll be using a top-down approach. So at the beginning, we just need to decide what's a good variable to put at the root. And once we make this decision, we then kind of naturally have two problems that are the same as we started with, right? We have some function that reaches this subtree, the original function restricted with x7 being -1. And we once again ask, okay, what's a good root here? And similarly on the right, we ask, okay, what's a good root here? And we continue down. So this definition of a good variable is something we call the splitting criterion. And by looking at kind of this top-down approach, we essentially reduce the task of building a decision tree to the task of designing a splitting criterion, to deciding on a single variable at a time. And just kind of intuitively, we want some notion of importance or relevance to put a bit, like we want a variable that's very important or very relevant. And later in the talk, you'll see one example of a splitting criterion that ends up working well. Okay, so we can design these splitting criterion. And when we're designing them, we want to kind of have some basic setup. We have some questions about the basic setup. So just to formalize it, the splitting criteria is an algorithm that takes in a function and it outputs a particular bit to look at, what are the variables. So the first question we might ask is, what access do we get to the function? So kind of in learning, you might care about random examples. In other settings, maybe you have query access. You can pass in any input to the function and you'll know its output. Or maybe in some settings, you actually have the description of the function in some form, and you could do more than just query it. You can inspect it and see, I don't know, maybe you have a half space and you can look at the individual weights, for example. In this talk, we're going to focus on query access. But we do have some other work, for example, for random examples. This will just be the focus of the talk. Other things we want to keep in mind is what efficiency constraints do we have on our splitting criterion, both in terms of kind of in our case, the number of queries it makes, and also in terms of time. And then what guarantees can we make of the top-down tree that results from using the splitting criterion repeatedly to build a decision tree?
So, Guy,
yeah.
query are value queries, just value queries.
Yeah. So you pass in an input, and then you know the value of f on the input.
Perfect. Got it.
Yeah. Thanks for the question.
So I have a question. You're going to be taught. You can easily build a decision tree that's exactly models the function in linear size. But right? Oh no, sorry. It's still going to be exponential size. Yeah.
Are you talking about you querying all the variables?
Yes.
Yeah. So that'll be exponential in n, and maybe like the decision tree is much smaller than that. Kind of the optimal one.
Are you going to relate this at all to BDDs?
That won't be a focus of this talk, but for BDDs, is there some, like, can you build the most efficient one because you kind of get repeatedness somehow?
Yeah, BDD, I guess it's a completely different problem. You want to model it perfectly. It's just model a Boolean function exactly. But never mind. You're going to be talking about things like approximate modeling a function, I guess.
Yeah, that's a good question, but yeah, we will be relating to BDDs here. Okay, thanks for the questions, and yeah, feel free to pop in with questions. Okay, so throughout this talk, it'll be convenient to be able to refer to kind of the top-down tree. So this kind of takes the intuition from the previous slide about how we build trees top-down and formalizes it. So for a splitting criterion S and for a depth D, and then some function f, we have a top-down tree. So the constraints we have with this tree is, one, in this talk, we're just going to assume everything is a complete depth D tree. So you split all the way until you are depth D. And then we're going to have, for every path, the variable queried at that path is equal to the splitting criterion of f restricted to just inputs that reach the path. So for example, if we're looking at the root, then pi is kind of the empty restriction. So we split on whatever the splitting criterion says of f. But then as we make other splits, we just look at inputs that reach there and ask our splitting criterion, what's the most appropriate variable for that subfunction? And then for leaves, we do something, well, it's pretty simple. So our functions output 1 and -1, and we just kind of put the best leaf there. So if more than half of the inputs that reach this leaf are labeled 1, then we will label that leaf with 1. And similarly, if more than half are labeled -1, we'll label that leaf with -1. Okay, and now an outline for the rest of the talk. So I call this next part 0 because it's a single slide, but it will be our main result. We'll kind of, I'll tell you the existence of a splitting criterion with some really nice guarantees, but I won't go about proving it or telling you how it works. That'll be reserved for part 2. So then in part 2, I'll tell you what the splitting, well, kind of a simpler version of the splitting criteria, how it works, and then give a proof sketch. And then in between those two, we'll go over some applications. And really the thing I want to emphasize in these applications is that they all kind of use the same insight, but they can be applied in many areas of computer science just because decision trees are so fundamental. Okay, and now for our main result, something I like to call a universal splitting criterion. So there's a efficient splitting criterion, S. Here, remember, we're working in query, we assume query access to F. So as long as f is close to some depth D decision tree, here D is a parameter that you can choose. So you kind of choose a D for which f is somewhat close to some depth D decision tree. The top-down tree at depth big D, which is polynomially larger than little d, will also be close to f. And how close it is kind of a function of how close the best depth D decision tree is. So if you choose a little d such that there is a very close tree, then the top-down tree should also be very close to f. And epsilon here is also a parameter you get to pass in. So just kind of to summarize this, as long as there is some good decision tree for f, we expect the top-down tree to also find a slightly larger, slightly worse, but still good approximation for f. And then for the applications, we'll need the fact that S can be computed very efficiently. It uses only polynomial queries in dn 1 over epsilon times log n, and time that is comparable. You need at least order n time just to specify a query. Any questions about what this result is saying?
Yeah, do you need to know little d up front as like part of the input to the algorithm?
Yeah, that's a good question. So in each of these applications, you don't have to assume you know little d because you can kind of search for it. You can like guess little d, build the top-down tree, and then kind of empirically estimate its error by just taking random examples. So you can like figure out what d you need to then get sufficiently small error.
All right, thanks.
But yes, so the algorithm itself, I mean, it kind of builds a sequence of trees, and you can just choose when to stop. So for each of these trees, you would like estimate its error, and then you would figure out what is a good stopping point for big D. And then we guarantee that your stopping point will only be so much larger than kind of the little d you needed to get comparable error.
Sure, thanks.
Okay. And now we'll dive into applications.
So, Guy, before you go there, the suspense is killing me. What is the splitting criterion? This mysterious splitting criterion that you talk about?
So the one I'll talk about in this talk is user split on the most influential variable,
Okay.
Which I'll define later, which is, I think, a very natural one. That only works when opt d is 0. And I won't talk about it much, but if you want it to work when opt d is not equal to 0, you split on the noisy influence. And I'll try to give a tiny bit of intuition, but I won't. But it kind of just gets rid of some adversarial things that can happen if opt d is not 0. But the two are very similar, and the analysis is fairly similar.
So in practice, wouldn't they use kernel methods?
Sorry, what do you mean by kernel methods?
Well, that you do linear cuts in high dimension.
Oh, yes. Yeah. So in this talk, we just consider Boolean inputs. But yes, so this work, some of it we don't know how to expand to kind of like you allow thresholds or kind of linear cuts. There is a particular formulation of it from learning that does have some nice extension to not linear cuts is what we proved, but we proved like you can have real inputs and then you can do a threshold of it. But yeah, so one thing is you can encode any kernel as a Boolean function, but now your input bits are not independent. And for all of this work, we assume kind of independence. You have some product space, but it's an open and interesting problem on how you can expand this to arbitrary distribution.
The user is allowed to pick a kernel?
Yeah, so the user has picked a kernel, but kind of importantly, we assume that all of the outputs of the kernels are independent. So this really works for Boolean functions, but I think for lots of practical scenarios, your kernel won't be independent, in which case we don't have theoretical guarantees, but we kind of have some evidence it might work.
So I just want to point out, there's a question in the chat from Miles about information gain.
Oh, yeah, I was just saying for your splitting, for choosing how you split, I thought information.
Yeah, information gain is used in practice, but the one we're kind of designing a splitting criterion here. It lines up pretty well with information gain when your function is monotone. So when your function is monotone, we can show that kind of these practical algorithms work. But then when your function is not monotone, you can show that that doesn't necessarily work, in which case we design a different one that does not correspond to information gain. Okay, any other questions or comments? Okay, I'll dive in. Okay, applications. Okay, so why is it really nice to build a top-down tree? Well, the underlying theme of all these applications is that we kind of have local access to the tree. What I mean is, okay, so we could build this entire tree, but maybe it's too big. The size of the tree is exponential in the depth, and maybe we need some reasonable depth, but a very large, then a correspondingly very large size. So the nice thing here is we can access kind of like what bit is queried at a node without building the rest of the tree. And I won't go into like the full locality we allow, but the really important thing for these applications is that we can compute T of X. So on some input, we can compute the output of the tree by only building a really small portion of it, which is the root to leaf path. So let's say we get some input. Okay, so the first thing we do is what's the splitting criterion of the root? And we say it's x7. And then we look at what is the x7 bit of that input. And if it's left, like in this case, we immediately don't have to build the right half of the tree. We've kind of already reduced our problem in half. And then we go to x4, we figure out, okay, what split do we want here? It's x4. If that's left again, okay, we go to the left and we're done. And we didn't have to build any of the right side of this tree. And for each particular input, there's simply like one path, and we only have to build that path. And this can be nice for some applications. So just this only requires O of the depth of this tree, calls to S, which once again is exponentially smaller than building the full tree. Questions about this? Yeah, go ahead.
Question. So what's wrong with just a depth 1 tree? If the answer is +1, you go one way and -1 the other?
Well, so your function might not be close to a depth 1 tree. So then, like, I mean, these are kind of like repeated depth 1 trees.
Because you're splitting on something, right? You're splitting on axis aligned cuts or some other kind of thing. I mean, somehow you've restricted the set of by partition, right? If you allow me to pick any kernel, for instance, linear kernel, am I allowed to?
Yeah. So we kind of assume that the bits you have are fixed in advance. So we formalize everything as just a Boolean inputs to Boolean outputs on some like fixed number of Boolean inputs. So that corresponds to some fixed number of kernels that are decided ahead of time.
So can you tell me what kernels you want, or what cuts you're going to allow? Axis or something.
Well, in our case, we're abstracting away the kernels. We just assume you have Boolean inputs, and we don't look at the kernel. So our work, like if your bits allow for a small decision tree, then we will find a small one, is roughly what we're saying. And we're abstracting away whatever kernels you might want to use. Okay. Does that make sense? So like if your kernels are sufficient to build a decision tree, then we also want to build one, but we don't look into what the kernel does.
Okay.
I should say that we make some assumptions that the kernels are kind of independent. So for many kernels, this won't work. But yeah, we just assume bits, which is kind of like the layer on top of kernels if you have some kernels.
So you're not allowed to pick kernels based on the data, the function.
I guess there's nothing stopping you there. You could have your bits dependent on the function.
Okay.
I have a question.
Yes.
So this local building idea, how do you, I mean, I can see how you can figure out like what path you'll take just by calling S repeatedly, but how will you know what the number you output at the end is? Isn't that the thing you normally have to store?
So you can also compute this live. So
okay.
So it's you take all the inputs that reach this path. So at that point, you just do random sampling. Here we assume everything is computed exactly, but you randomly sample points to that path, and then you see are they tend to be 1 or -1.
Okay, so you're gonna, but that's not guaranteed to be the same every time.
Yes, but I mean, if you wanted to, you could like just memorize it.
You could catch it.
So
okay.
yeah.
Okay, but all right, I see what the application you're talking about here is.
Yeah.
Thanks.
Also, for simplicity, I should say, I assume that this is the same every time. Similarly, if you do this in practice, the splitting criterion will have some randomness, but you can just cache it, and everything works if you assume a small amount of error in these computations. So this doesn't have to be exactly like if your expectation is really close to 0, then you can choose either -1 or 1, for example.
Gotcha.
Okay. Any other questions? Okay, so the first application, which will be the property testing, and for this one, we'll basically use the property I just told you directly. Okay, so the question we're concerned with here is testing for DT size. So in property testing, we generally consider there's some property of the input we want to know. In this case, we kind of want to know if it's a small decision tree, and we want to make few queries to it to determine whether it satisfies this property or is far from the property. So our exact guarantees are kind of incomparable to a lot of the prior work, and I'll tell you here what they are. So once again, we assume we have query x to some function, and I'm doing here things in terms of size just because that's more comparable to prior work. But you can translate everything to depth pretty easily by just kind of doing the log or the exponential to get between the two of them. So we have some Corollaries of this, and we want to say, okay, if f happens to be very close to some decision tree of a size that we specify, then we output yes. And if f is far from all decision trees of a larger size, we output no. So there's a gap here. If f satisfies neither of these, then we make no guarantee in our output. So we have a separation between our yes criteria and no criteria. And the nice thing here is it's very efficient. So the number of queries we need is polylogarithmic in the size and then times log n. And the number of time is the same with an additional n factor. This adds to a long line of work on testing decision trees. Okay, and now some comparison with prior work so you can see kind of how this stands up. So there's lots of differences, so I'll try to go one by one. So for the yes criteria, in this case, ours is slightly stronger. Epsilon is a user specified parameter. We could specify epsilon equals 0 to recover their yes condition. On the other hand, our no condition is weaker. So they have the same size for yes and no. So the only gap kind of in their yes and no conditions is from this epsilon. So they'll you could have a tree with error epsilon over 2 for size s, like the optimal tree of size s for some function could have error epsilon over 2, in which case they're in a gap. And that appears kind of a similar gap appears for ours, but they don't have a gap from a function being close to a size s tree, but say, or not being close to size s, but being close to a size 2s. So I guess the point is there are 2 gaps in ours and only 1 gap in there between the yes and no conditions. And then the complexity also is incomparable. A lot of the kind of the existing work really focuses on getting queries independent of n, which we do not get. But in exchange, we do get an exponential improvement on the size. So if you think of your decision tree having size, say, polynomial in your number of bits, then this is a big improvement. But in a setting where s is really, really small, then this might not be an improvement. And in time, kind of a similar thing, but the improvement is doubly exponential in the size dependence. Okay, any questions about how this stacks up with prior work? Okay, how do we do this? Instead of giving a tester, we actually give a reconstructor. I'll tell you what that is. A reconstructor implies a tester. It's pretty well known and it's not too complicated. And I'll try to say a few sentences about it, but I won't go into details. Reconstructors are really cool. I don't know. At first glance, it might be surprising you can do this. So let me try to tell you what a reconstructor is. So okay, so we have Corollaries of some function, and we assume that function is close to some size s decision tree. So let's say it has 1% error to a small decision tree. But importantly, these 1% can be arbitrary. So maybe exactly representing f requires a huge decision tree that's incomparable to s. Okay, but now we want to answer queries to a function close to f, here a function t, and we want to guarantee that every query we answer is consistent with some decision tree of bounded size. So now there kind of can't be any error relative to decision tree. They all have to be consistent with this decision tree. So kind of graphically, let's say this is Bob and this is Alice. Bob is asking Alice for queries consistent from some decision tree T. And Alice makes queries to F, of which most inputs are consistent with the decision tree that's a little smaller, and kind of fixes a few of them, but only a small fraction as Alice goes, in order to make them all consistent with some big decision tree. And importantly, Alice can't look at all of F to fix a query. Alice can only make very few queries to F and then figure out, okay, how do I fix this particular input? And kind of the number of queries we need and the amount of time we need to answer each question for Bob is the same as you saw in the last slide. Questions on what a reconstructor is? Okay, and then how do you go from reconstructing to property testing? The algorithm is pretty simple. I don't think I'll go into any proof, but basically you simulate Bob, you take a bunch of random samples and you ask Alice, so you get queries from T of X, and you check if T and F are close. And then if T and F are close, it means the function must be consistent with some small decision tree. And if T and F are far, then they can't be. And the proof is kind of, you just walk through all the cases and all the cases work, and you add a tiny bit of error, but everything ends up okay. Okay, our reconstructor, well, it's very simple given everything we went over. It's essentially the key insight from the kind of the beginning of applications. We look at F to support queries from the top-down tree for f. So we just have to, given some input, we have to efficiently compute like what is t of x, where t is a top-down tree. And this just requires computing the root to leaf path for t. And this only requires O of big D calls to the splitting criterion, which is like roughly log s. And each one takes only roughly log s queries or polylog s queries. So we get all the efficiency guarantees we want. Yeah, this is fast, but any questions about kind of the idea behind this reconstructor? Okay. One nice thing here is that we can get reconstructors and testers for lots of other properties. The reason is that every, well, I'll just give you an example. Every function that is like exactly equal to some small step decision tree has like kind of a Fourier degree. So for example, like for Fourier degree, it's the degree of the highest term in its Fourier representation. And that is like quantitatively related with the optimal decision tree depth. So these are just like people have already worked out that your optimal decision tree size or depth is related to a bunch of other quantities. And therefore, we immediately get reconstructors and testers for those. I'll just kind of give you one example. So if you assume that your function is close to some degree d polynomial p, then we can give you query access to some degree d to the 7th polynomial. This just comes from kind of using how related dt depth and degree are and plugging in some stuff, q. And kind of what we're doing behind the hood here is we're actually just building you a decision tree, but because we know the decision tree is related to the Fourier degree, we immediately get a reconstructor for polynomials and a tester for them and all those other properties as well. Okay. All right, application 2. This will be to machine learning and explaining black box models. So pretty different from the last one, but the algorithm you'll see is quite similar. So, okay, so the setting here is, think of, you have some opaque classifier, maybe you have some really deep neural network, and you can easily compute its classification on some input, but you want some understanding on why it makes that classification. So 3 authors in 2018, Ribeiro, Singh, and Question, proposed this concept of an anchor. And I'll tell you what an anchor is on the next slide, but roughly speaking, it tries to highlight a portion of your input, like some subset of the features that explain the classification. And they ran various experiments. So here is one you can see. So you have this image. Want to enter your classifier and see that the classifier classifies it as beagle. You want to know why? Well, the anchor kind of highlights a few random things, but mostly kind of parts you would expect, like the face of the beagle, a little bit of its fur. And this gives the user some intuition. OK, this was what the classifier looked at in order to make its classification. OK, so formalizing the definition of an anchor. If you've seen certificates in complexity theory, they're quite similar. So in an anchor, an epsilon error anchor is a subset of features. So kind of in the last slide, think a particular set of pixels such that, OK, so you remember you have some particular input x. And the guarantee we have is most of the inputs that kind of share all these features with x have the same classification. But in other words, like the probability that a random different input that shares all those features with x is classified differently is small, is less than epsilon. Question on this definition? Okay, so in the original paper, RSG did a lots of really cool experiments. For example, what you saw on the last slide, and they gave an algorithm for finding anchors, but without provable guarantees. And they also did some user studies. So they kind of they like had people and they asked them, do you like these explanations? How do they compare to these other explanations from other competing methods? And people tend to like anchors. So our work here is an efficient anchor finding algorithm with formal guarantees, but in like a setting where we kind of assume independence of features. So in practice, like the formal guarantees might not apply, but hopefully the algorithm still works well, even if you don't make those assumptions. Okay, so what's our algorithm? Well, it's very similar to what you saw. So we build a top-down tree, or not all of it, but like we have X to the top-down tree. We build the root to leaf path, and we just take the features on the root to leaf path. I guess I'm using features and variables here interchangeably. They mean the same thing to me. I'm using features in a machine learning context. Okay, so like if our input was classified -1 according to this path, then our anchor is x4 and x7. And the reason you think this might work is because in the top-down tree, it's true that all inputs that follow this path are classified the same way. So this is kind of a 0 error anchor for t. And then t is close to f, so we expect this to be a low error anchor for f, which is kind of what we care about. T might not be exactly equal to f, and we want anchors relative to our like more complex classifier. So the kind of the informal theorem we give is that if we can guarantee our black box opaque classifier has small and accurate anchors for most inputs, and this algorithm will find small and accurate anchors for most inputs. So you have to make an assumption that your function is explainable via this method, but as long as it is, we'll give you slightly worse explanations than the optimal ones. And then a key technical ingredient here is Smythe's theorem from complexity theory. And basically this says if your function has good anchors, then it's also close to some decision tree, which means we can then just use our kind of guarantee for top-down trees to say, okay, you can build a tree that is close to it. Questions about this? Okay. Our third strategy is from a different field. This will be query strategies for priced information. But you'll see that kind of the algorithm is pretty similar. Okay, so the context here and how we formalize it, and this has been formalized in a few different ways, but this is ours. So we have query access to some function. And now we have an input, but we don't actually know the input. We kind of start with all of the variables being question marks. But at some cost, we can inspect a particular bit in this input. And our goal is to compute the value f of x as cheaply as possible. So just like an example on this, let's say this scenario, let's say our algorithm decides, okay, the last bit seems really useful, so it can query at the cost of $1. And then it might be, oh, given that that was a 1, I think the first bit might be really useful. So okay, it'll pay $2 more, and now it'll get the first bit. And it could keep going and querying, but maybe it'll say, oh, I've seen enough. I don't actually need to know the middle bits. I'm already pretty confident that the output of this function is 1, and so it outputs 1. And then it didn't have to pay kind of an extra $3 it would to reveal both of these bits. So if you're kind of wondering, give an example, one I like to use is, like, say you're a doctor and you want to know whether a patient has a disease. You have like maybe many tests you could run. And using your doctor knowledge, if you knew the result of all of these tests, you could be pretty confident whether or not the patient has the disease. But these tests have some cost, maybe monetary, maybe potential side effects. So you don't want to run all the tests. So in this case, you might want to design a query strategy in order to determine whether they have a disease. I should also say, if these prices are constant, this is essentially the task of building a decision tree. But then it gets a little more complicated if you can have variable prices for each bit. Any questions about the setup here? Okay. So our objectives are, so one, we want an accurate strategy. So we define the error of a strategy to be like you take some random input, and then what's the probability that the strategy's output differs from the function. So we do allow a little bit of error here, but we just want to minimize it. Of course, we want to be computationally efficient. So we want our strategy to be fast to evaluate on a computer. And we also want cost efficiency. And we measure ourselves against the best possible cost. And we do this for expected cost. So what we mean is, okay, the expected cost of a strategy is pick a random input. And then it's like for each input, your strategy has some cost, how many dollars it used, and what's the average over all inputs. And we always benchmark ourselves against kind of the optimal cost. So the optimal cost depends on your epsilon. If you want smaller error, your optimal cost might be larger. It depends on your function, of course, and it depends on like the cost of each bit. But once you know all of those, you get some optimal cost. And our goal is to have a strategy as close to optimal cost as possible while still getting essentially epsilon error. Okay. And a key novel feature of our work here in comparison to lots of prior work is lots of prior work assumed your function has some particular format. So for example, maybe we assume your function is like a half space. And then, okay, given that your function is a half space, here is a query strategy that will work well for it. And generally not only assuming that your function falls within this class, but that you can like inspect it. So you can like look in and you can see, okay, in the half space, these were your weights on each variable. So in contrast, our strategy just uses black box access to the function, and it doesn't need to assume it falls within some particular class, though that will kind of affect the quantitative strength of our result, which we'll see momentarily. But like as the example I gave you, if your strategy is like knowledge in a doctor's brain, then it's not clear that it falls exactly within one of these classes, and you probably can't inspect it and like figure out the weights of the corresponding half space. But you can query the doctor. You can ask them, okay, if these were the test results, do you think the patient would have the disease or not? Okay, and our main result is if you have query x to some function and you have an error parameter epsilon, we can give you an O of epsilon error strategy with the cost a little higher than optimal. The approximation ratio is roughly the total influence of f. Total influence will pop up later in this talk, so I'll give you a formal definition. But it's a measure of the complexity of f. So if you have some very complex function, then maybe our strategy won't give you a good approximation ratio. But if your function is somewhat simple, then you can get a nice approximation ratio. And then a nice thing is people have spent lots of blood, sweat, and tears bounding the total influence of various function classes. So if we assume your f is within some class, even if we can't inspect it, even if we just have query access, then we immediately get a bound on the total influence, which immediately gives us a bound on the approximation ratio of our strategy. Any questions here? Okay. So just corollaries, and these are all easy for us because people have already bounded the total influence, so we just plug in these bounds. So just some examples. If your function is a size t, depth d circuit, you will get an approximation ratio of log t power d. If your function is the intersection of m half spaces, you'll get an approximation ratio of square root of m log m. If your function is monotone, you get an approximation ratio of square root of n. And I just went through those quickly, but I guess the point is someone has bounded total influence, we plug it into our main theorem, and it's an immediate corollary. As far as we know, these are the first non-trivial guarantees for each of these classes. Yeah, so we didn't have to do too much here to get it. Okay, and then the high level idea is, once again, we have this decision tree T, and we're going to build the root to leaf path for T of X. This is the top-down tree, and we're only going to query variables along that path. The difference here with the prior applications is we don't use the splitting criterion directly because we pay a different cost for each variable. So we modify the splitting criterion a little bit to take into account that cheaper variables are good to query, even if they might not be too informative. But this ends up being not like the modification is pretty simple and the analysis ends up working out. So yeah, so we modify it to cheaper variables and then we just query along the root to leaf path. Yeah. Okay, that concludes applications. Any questions here? And I'll just check how much time we have. Okay. This ends in about 17 minutes. Is that people usually end around 1? Okay, I see nods. Okay, our splitting criterion. Okay, so I promised you this, that there is an efficient splitting criterion that as long as your function is close to some decision tree, the top-down tree of a slightly larger depth will also be close to it. What we'll prove to you, or at least proof sketch, is if your function is exactly equal to some depth D decision tree, then you'll build a very close one. So we'll assume opt D being 0 in this. And this just simplifies the proof and allows a slightly different splitting criterion, which is a little simpler. But a lot of the concepts will go through in the case where your function is only close to some decision tree rather than exactly equal to it. So kind of in this setting, you have to choose little d such that you can get this distance 0. Okay, what is the splitting criterion? Well, if you remember, kind of the intuition from before is we want to choose a variable that is important or relevant to the function. So we use the influence of a variable, which was kind of designed for kind of exactly measuring these sorts of notions. So the influence of a particular variable, kind of xi with respect to a function f, is the probability you take a random input that flipping that particular variable changes the function value. So put differently, the probability that you fix all the other bits, and you still have to know this last bit in order to determine the function value. So kind of like if a variable has high influence, you can't really get around querying it. And then with this definition, our splitting criterion is simple. We measure the influence of all the different bits of all the variables, and we just output the one with the largest influence. Any questions about the splitting criterion? Okay.
Your function's the parity function, then what would you do? You just, I guess, do one bit at a time, I guess, right?
Yeah. So in the parity function, all the inputs have influence 1. So you just query them in arbitrary order, and then the optimal tree for parity also requires querying all the bits. So.
But suppose your decision tree allows you to do more interesting, calculations over GF2.
Yeah. So we're really assuming we only have access to the bits, like whatever. So we just assume you can only query a single bit at a time. What I was talking about kernels earlier is you can kind of represent a kernel as a bit. So like if a priori you decide maybe there's you can like do a parity, then maybe there's a smaller decision tree. But here, like when I talk about the parity tree, I'm assuming that you don't have any, you can't do calculations with GF2. You just pick a single bit at each time.
So throughout the whole talk, I mean, the assumption is that the class of decision trees is fixed, right?
Yes. Yeah.
There's say axis aligned cuts or some other thing, right?
Sorry, can you repeat that?
Axis aligned cuts, like this worry about a single bit and cutting that bit. That would be an axis.
Yes. Yeah. Yes. So that is what we allow. You can abstract other things into this framework, but really you then lose some nice things. So you should think of it as just, we query a single bit.
Yeah, so you can't have Gaussian kernels or anything other thing, or axis aligned cuts or any of those. I mean, any other kind of linear cuts. Yeah, no, all of our splits are just a single bit. And we assume your function is close to, like, kind of in this assumption here, we assume you're exactly some decision tree that has these axis aligned cuts. But how many in practice and people in practice do that? Because you said this was related to practice. I would imagine that they allow much more exotic cuts, right?
Yeah, so that we were taking intuition from practice and using it to decide, okay, like, do we want to build trees top down? The focus of this talk is these, I guess, like practical / theoretical questions, where maybe you're happy to assume Boolean bits. So for example, in like the application to querying priced information, you don't want to do any complex kernel because that requires making lots of queries. So in that application, you need axis line cuts because you only want to query a few bits or like very cheap bits. So kind of kernels will be bad there. In terms of slightly more complicated cuts, we do have a little bit of work. It's still axis aligned, but kind of allow arbitrary threshold and real valued features with some assumptions for like kind of machine learning, like where you want to learn a model. But in this talk, we're not focusing on any of that.
Okay. Thanks.
Thanks for the questions. Okay, so splitting criterion here is max influence. Okay, the proof is not too complicated. So, okay, we can think of top down as building a sequence of trees, each of slightly larger depth. So we start with a depth 1 tree, then we have a depth 2 tree, all the way up till depth big D. And then we can kind of track the progress we've made at each step. That's why I think of it this way. So we want to claim, once we get to big D, our top-down tree will be close to the original function. And the way we do this is we define a potential function from these trees. So each tree will have some potential. And we're going to argue that at each depth, either we're already done, either this decision tree is close to F, in which case we're happy because our goal is to output a decision tree that's close to F, or the potential goes down by a significant amount. And eventually it'll reach 0, in which case we'll also be done. Okay, and I haven't told you what the potential is yet, but okay, now I will do so. So in words, the potential is something we call the total influence of F with respect to T. The total influence is a pretty common definition. So the total influence of a function is the sum of all the variable influences. And then our potential is kind of an averaging of this over the tree. So what we mean is, okay, you have some tree. The tree has many leaves. Now consider a single leaf. You have like a subfunction of F of just the inputs that reach the leaf. So we can compute the total influence of F restricted by inputs that reach this leaf. And then we average this over all the leaves. So just some quick intuition. If your total influence is really small, then this particular subfunction must be close to constant. And if this particular subfunction is close to constant, you're happy because the top-down tree will choose the best labeling of this, either 1 or -1. And if FL is close to constant, then the best labeling will be a very good one. So this potential, when it's low, we're pretty happy, which is something we want because we're going to argue that it gets low. Just some quick observations about it. The potential of the empty tree is just the total influence of F, because you kind of only have the single restriction, which is like the empty restriction. And a fact is that all depth D decision trees have total influence at most D. So we get that our potential doesn't start too large, which is nice because we're going to decrease it and we want to argue it gets to 0. And this potential for any tree is at least 0. So we can use that to say, if we're decreasing by a lot each step, you can only decrease so many times before you're done, before you would have to get negative, which is impossible. Any questions? Okay, so and now we're going to compare our potential and our splitting criterion and really see they go hand in hand. So let's say we have the top-down tree of some depth k, and then we split to make the top-down tree of some depth k plus 1. So we want to know how much the potential goes down. And here we write the potential is using their definition. Okay, so the potential here is the average over each leaf of the total influence. Sorry, that should be a capital I. The total influence of F subfunction L. And then in the right tree, we have a similar thing. Here we get the total influence of each of these subfunctions, but we want to correspond it with something from this tree, so we can compare these two. So we're gonna look at this total influence versus kind of the average of these two total influences. And if we average that over all subfunctions, we'll get how much the total influence changed. So here's a fact. So the influence of this function, f restricted by this leaf, which is the same thing we have here, is equal to the influence of just the variable you queried here, plus the average influence, total influence of each of these functions. So kind of within this area, the total influence decreases by exactly the influence of the variable you query. And it's not super surprising this is the case because total influence is kind of summing up influence over all variables. So when you query a variable, maybe it's not surprising that total influence goes down by exactly the influence of the variable you queried. Okay, so if we just average this over all inputs, all leaves, we get that the decrease in potential is exactly the average influence of a variable we queried. So it kind of, the conclusion we can make from this is maybe a chicken egg problem. We could have, instead of designing our splitting criterion first and then find the potential function, we could have designed the potential function to be like this, average total influence. And then our splitting criterion is just greedily choosing the variable at each step that decreases its potential function the most. And the amount it's decreasing it by is exactly this influence, which makes things easy to work with. Okay, so our task is to show that each variable has each step we can split on a variable with large influence, because then we can make a lot of progress. And for this, we use a very nice inequality, OSSS. The O here is your own Ryan O'Donnell. So the name of this paper is Every Decision Tree Has an Influential Variable, which the name kind of makes it seem that this will be useful for us in this application. So what this inequality says is that, let's say we have a function, and we know it is computed by a depth D tree, where here we want D to not be too large to get a good bound. And let's say the variance is also not super small. Here the variance kind of is how far you are from constant. So if your function is not far from constant, and your function is exactly equal to a depth D decision tree, then there is a variable with high influence. And how high the influence is depends on the variance of your function and the depth of the tree. Yeah, I guess before I go into more, any questions about what this inequality says? Okay, so we can pick a variable with pretty high influence, and we're happy because then we can make a lot of progress in our potential. Okay, and now kind of everything comes together into a one-slide proof, or at least proof sketch. Okay, so we're building this top-down tree. And when I say so far, I mean, okay, say we have some particular depth. So at each depth, we ask, okay, for this tree, is it true that on average, the subfunctions are close to constant? Okay, let's say that question is yes. Okay, then the subfunctions are all close to constant, which means the top-down tree will be close to F, because if each of the leaves is roughly constant, then you can like put down a good approximator each one, and on average you get low error. Okay, what if the answer is no? Then, well, we're going to keep making these splits, and now we'll track how much potential gain we get. So, well, we need to subtract. We need to see this quantity, which is the average influence of all the variables we put down. So this I is what our splitting criterion chooses. But in our case, our splitting criterion chooses max influence. So this I is just the function with max influence. Sorry, there should be an FL here. Okay, and then we use OSSS. So we say, okay, we know that there is a variable with influence, at least variance of FL over D. So based on our assumption here that we're in this second case, the average variance is kind of large, and we can just use linearity of expectation to say, okay, the progress you make is at least epsilon over D, which, well, that's what we wanted to show from the beginning. The conclusion we can make is that when you increase the depth by one of the top-down tree, your potential decreases by at least epsilon over D. Okay, we started at potential at least D. So if we set big D equal to D squared over epsilon, then either we hit this case at some point, in which case we're happy, or we never hit that case, in which case our potential is 0. And we must also be done because our potential can't decrease anymore. So we must already have, well, we must then essentially be in this case. Okay, that is a very quick one-slide proof, but any questions? Okay, I think I'm nearing end of time. So I'll just quickly summarize. Well, anyways, I'm also nearing end of slides, so that's kind of good. All right, so we've shown that there's a splitting criterion for which your function is, if it's exactly a depthy decision tree, then we build a slightly larger decision tree that will approximate it. The case when you're not exactly a depthy decision tree, but you're only close to one, requires a slightly different splitting criterion. You can show that splitting on influence here can be really bad, but if you split on like a smooth version of influence, everything works out fine. And I guess quick one-slide intuition on why that's good. Okay, this is very hand-wavy, but I like this picture. Maybe you will too. Okay, so let's say this is your function. And okay, for now, let's assume F is a depthy decision tree. So you can think of it as, okay, you have inputs, and then your outputs here are like some very simple function of the input because you are a small decision tree. Okay, but now let's say you're allowed to switch 1% of the inputs, so you're not exactly a depthy decision tree. So now you get this picture where, okay, like you can kind of make out the simple thing, but you have these like kind of spikes in it. And it turns out these spikes are like kind of exactly what we don't want for this analysis. So G doesn't have the properties we want. Okay, but now let's say we smooth F. I mean, this is a graphical depiction in 2D, so this is not the same smoothing we do kind of over a Boolean cube, but here, well, this is just a Gaussian kernel, but yeah, just like some smoothing of F. Okay, so this still looks kind of nice. And if you smooth G, okay, I mean, the perturbations, what you changed of G from F like still matters, but now it seems to matter a lot less, and you don't have like these wild spikes. And it turns out that not having these wild spikes makes the analysis fine, and you can show that kind of in the smoothed view, things still work out okay. Yeah, I don't have a lot of time here, but I guess the high level idea is smoothing things makes it nice. It makes it work, even if you're not exactly a depthy decision tree. Okay, just to summarize, this was what we showed. Kind of, we told you about a universal splitting criterion that we get some nice guarantees in the top-down tree, and then we gave 3 applications to different areas of theory, showing how we can use it. And just some parting thoughts. So decision trees are very simple objects, and we needed that here because we wanted to make a very general statement that as long as you are close to some decision tree, we can build you one in a very particular format, and we can we kind of have a chance of doing that because they're simple, but they're also fundamental. They like appear all over computer science, and kind of the end result is that like a little bit of insight into what we can do with decision trees can lead to lots of different results down the line. So a parting question is like, are there other things we can understand about decision trees or similarly simple objects that we can then use to have many applications? Okay, thank you very much. And any questions?
Yeah, thank you for the talk. Yeah, a question. This whole talk, you've been assuming that, sorry?
No, I didn't say anything.
Yeah, so this whole talk you've been assuming that your inputs have been drawn from -1 + 1 to the end uniformly at random. What if we break this assumption? What if we say, okay, there's some known distribution over which the inputs are drawn? Does that change things or?
Yeah, so OSSS, I think the inequality we use to prove our thing holds for product distributions. And my guess is you can probably construct adversarial examples where it doesn't work. I haven't tried to do that myself, but yeah, so we need at least product distributions for this thing to work. But maybe there is some other assumptions we can make and get some guarantee that would work out well. But yes, we do need assumption. I haven't looked up the detail for product, but I don't see any reason why product would be different than uniform. Things I think tend to transfer with just like a little painful work. But for non-product distributions, then yeah, unknown how to build a splitting criterion.
I see. Okay.
So what about non-Boolean domains? So in the same count, everything will work for non-Boolean domains?
Once again, I haven't worked it out. We assume like a finite domain, and now your decision tree, like, you query something and you have, let's say, 10 possibilities and you have 10 branchings. Once again, haven't looked out the details, but I think things should be fine there. OSSS like has some similarly generalization to that, and I think things should work out.
So, and if you assume some structure on the function, my favorite structure is submodularity, but one could assume subadditive, something like this. Does that help a lot, or is that does it make the problem trivial in this case?
I'm not sure for either of those two cases. One thing that would fit very nicely with ours is, some natural functions might have low influence, so that would just make our bounds better. If whatever you assume has low influence. But yeah, I think, so definitely an open question of, if we make additional assumptions about our function class, then what's the best we can do? I mean, I don't know if what we did here is the best you can do, but I guess like unknown how these assumptions can help you. Like in our proof, I guess the most natural thing is, are you either high influence, or can we guarantee you have a more influential variable than we assumed? So kind of those are the two things that play into our bound. But there might be some other splitting criterion, which you can then make some additional assumptions that help.
So actually, on that note, something you said, so is this you showed a d squared bound, right, for the zero error case. Is there some reason to believe that this is the best you can hope for? Can you get, are there lower bounds that one can?
For this particular splitting criterion, yes, we can construct an example where you get d squared. But for other splitting criterions, unknown. I think, so my understanding of the lower bound work is, it's in terms of size, not depth. But if you translate it to depth, then kind of the result is it should be NP hard to exactly build a tree that like gets 1 times depth. But even 1.1 times depth is unknown. As far as I know, I haven't like looked through all the literature there. Right. But it does seem very hard. So yeah, I think that's a very interesting question of what is like the best thing that we can do here. Also in the opt d not being equal to 0 case, we get d cubed, not d squared. But I guess those are like kind of the same class of functions. They're both polynomials.
Perfect. Thanks.